nanohub.org.
Online simulation and more for nanotechnology.
Last speaker is Zheng Liu, who is, he's really been one of the people really pushing forward not just the well-established 2D materials, but really expanding our horizons on what kinds of 2D materials are out there and what could potentially be interesting, and how we would make all of these different things. So I am curious to hear what materials we should be looking at next and how we're going to find them. Take it away.
Thanks, Nether and Irene, for such a fantastic workshop. I'm pretty happy to attend it and share our recent results on the new materials. Okay, I was intended to talk about the machine learning, but after I took a look at the schedule, I found most work about the synthesis of new materials. So I decided to talk more on the materials. Okay. Like the 2D TMD libraries, the 2D magnet, and also the ultra-high ground boundary 2D materials. And in the last part, we discussed a bit on the machine learning-driven growth of the 2D materials or the novel materials. Okay. So we know that there's a lot of potential applications of the 2D materials. Just Lansing mentioned, right, in the electronics, there are great potential applications that we may pursue using the 2D materials. Apart from them, we can also use the 2D materials for electronics, for the thermal management, so on and so forth. So I won't go to details, but I believe currently the most problem is the most challenging for us is how to make high quality, large areas 2D materials. So now there's three main methods, right? The mechanical formulation that we can produce really high quality, but the output is pretty low. But liquid formulation is pretty good for the battery and the catalytic applications, but the quality is still not that high. So a lot of people, they are using the deposition method, such as the CVD method, CVT method, and MOCVD. So for example, for CVD method, we can produce reasonable good quality materials and large scale in large scales. So that's quite promising in many applications. So most of our materials will be prepared by this CVD method. In fact, there are a lot of variations in CVD furnace. Here, I just show an interesting one. What we did is we purchased a micro oven here. Okay, this is a micro oven, very cheap. And then we drill 2 holes in the micro oven. Then we inside cause tube. Okay, after turning it on, you will see that a lot of plasma inside, right? So this simple setup, we can achieve a really high temperature. I think above 1,500 degrees. And we can use it to produce some high melting point 2D materials. Okay, so talking about the materials we are making, that we starting from the sulfide like around 10 years ago, and then we step into the selenide and the tellurides. A few years ago, we demonstrate a library of the TMD materials. So as mentioned by Nancy, I believe there's 2 directions that the community can go. First one, in terms of method, I think people, they are looking for some high throughput method to make the materials into large scales. And also, I will discuss how to use machine learning to reduce the cost, reduce the manpower. On the other hand, the material itself, we want to make a wafer size material, low ground boundary, high quality, low defect. Okay, so we have been produced like more than 100 materials, and based on them, there are a few applications, a few directions in our lab. For example, we are keen on the physical property of the materials. And also we're also using the 2D materials as a model system to look at the interface of the electrochemical reactions. And then move on, we are also looking for the applications of 2D materials like the transistors and the new CMOS architectures. This talk focuses on some of the new materials and also this electrochemical applications. We're using 2D materials catalysis. Okay. So the TMD have been discovered after the graphene boron nitride, right? Because it's a really good 2D semiconductor like a molecular sulfide. Our lab has been working on it for a long time, okay, a few years. And turns out making a new material is not an easy job. We have to spend 1 year or even longer time to find the best parameters to grow different materials. So I talked with my student that is there any way that we can use the general method to produce the 2D TMD, 2D materials? And that student had really good background on ceramic industry. So he knows in ceramic industry, people use melting salt to lower down the melting point of the precursors. Most of them are oxide, right? So we are thinking that can we borrow this idea to the growth of the TMDs, right? And if you look at the growth of the TMD itself, there are the two key parameters, right? One is the nucleation density. We have to make sure there's a nucleus on the substrate so that the reaction can happen, so that we can have the materials. And the second one is the reaction rate. With a low reaction rate, the material grows in the small size, small domains. And with a high growing rate, a high reaction rate, we can have a really large scale of the materials. So the best combination is what? It's low nucleation density, but with a really high reaction rate, so that we can have large scale materials with a low defect. So, but unfortunately, okay, like 5-6 years ago, it's very challenging to grow most of the TMD is expected for the molecular sulfide tungsten selenide. And the reason is what? The reason is some of the TMD materials, such as the hafnium-based, titanium-based, right? The precursor had a very high melting point, so more than 1,000 degrees, right? So go back to the idea of melting salt. So we just borrowed the idea to the growth of TMD, and we demonstrate that we can grow tons of the TMDs. So almost all the TMD can be grown by adding melting salt. And here shows the photos of TMDs. I want to highlight that for sulfide and selenide, okay, it's quite easy to grow into monolayer, a few layers. However, for telluride, it's not that easy to control. So most of them, there are few layers. And working with Kazu, we figure out that there are 4 primary phases in the 2D TMD monolayer: 1H, 1T, 1T prime, and 1T double prime. We spend a lot of time with this, tons of TM samples, 2 years on it. Okay, not only for the binary TMDs, we can also use this method to grow the ternary TMD, showing here with different elements, from 3 elements to 5 elements. So that's unlimited, I can say, combination for the alloy. And here I show a very classic alloy, which has 5 different elements in quite small areas. So this is a homogeneous alloy without any phase separation, and in such a small areas. And I want to share is that this is not the limit of the CVD method. So in our recent work, we can put even 9 or 10 different elements in the monolayer structures. So in these small areas, there are a lot of elements inside. Okay, although we really don't know what it can be used for, but material side is quite amazing to achieve this. So next step, we are looking, we want to figure out what is the role of the salt, metal salt. So by working with Boris, right? Boris did a really excellent job on this. They found that there is an intermediate phase of during the reaction, which we call the metal oxychloride. This compound can be formed during the reaction, and it's really highly active. So that some of the materials we can produce it into a large scale. Okay, this is a story about the TMDs. And recently, the 2D magnet is also a hot topic, right? There are a lot of potential applications on the 2D magnet. There are a few papers showing some possible candidates of this 2D magnet. And we are thinking that, is there any way that we can grow the 2D magnet? If you're looking at the periodic tables, we can find that these elements, okay, from group 3B to group 1B, they are possible candidates for the magnetic materials, and if they react with these chalcogens, sulfur, selenium, tellurine, can we produce the 2D magnet? So we try this, and it turns out, okay, there are a lot of new phases can be formed during by the reaction of the two groups, right? Here we show that the materials, the possible candidates, and those materials in bold, we already produced in our lab. Okay, how many of them? Okay, just take the iron as an example. So for iron-based 2D magnet, here shows the different materials, different phase of them. So iron sulfide, iron selenide, telluride, and also the alloys. So it's not the end. Okay, this material is FGT, right? It's quite popular 2D magnet recently. Even for the FGT, we can use CVD method to produce it, and found that at least there are 3 phases in FGT. So we can increase the ratio of iron, and you can increase the TC, which can be close to room temperature. So this is the story about the 2D magnet. And the third story about the materials is the ultra-high ground boundary 2D materials. So now we are looking for some people are looking for really high quality, low ground boundary density material for electronic material, right? However, ground boundary or defect, they have a different functions, such as in catalysis, right? People, they are creating defects, they are creating point defect ground boundaries so that they can enhance the catalytic performance of the materials. So we are thinking of that. Can we produce the materials with a really, really high ground boundaries? So we're starting with the silicon wafers or sapphire is also okay as a substrate, and then we deposit the gold cotton dots, the really small golden cotton dot. Okay, the size is a few nanometers. Then use them as the nucleoside. We grow the TMDs, and finally we can grow the wafer size of this ultra high density 2D materials, molybdenite. If you zoom in, okay, in a scale like 10 nanometers, we can still see a lot of ground boundaries there. Let's take a look. Okay, here, if you look at the Raman spectrum, right, because there is a highly grain structures, so the E2G peak has suppressed a lot, which indicating the interlayer interaction, interlayer vibration has been weakened a lot. Then we take a look at the atomic structures by collaborating with our collaborators. We figure out that we choose, okay, here, 1, 2, 3, 4, 5, 6 points of 6 locations, and we zoom in. Each of them shows really rich structures that consist of a lot of ground boundaries. So we found that the average size of ground boundary is around a few nanometers. It's less than 10 nanometers. So which means in such a wafer size, wafer scale materials, we have billions, even more than billions of ground boundary reserves. So here shows the details of the ground boundaries. Most of them are bilayer and monolayers, and this is there here shows the ground boundaries locations. Where are they? Okay, the question is how come we can form such ultra high ground boundary structures? So we propose that this climb and the drive mechanism, because of the surface tension difference for the two layer between the gold and the molybdenum sulfide. For monolayer, the surface tension is below. However, for the few layers a bit higher, so which result into the picture that monolayer growth of material will push. For monolayer materials, molybdenum sulfide, the gold job will climb onto the molybdenum sulfide. On the other hand, once we grow 2 layers, 3 layers, this molybdenum sulfide will push the gold to the edge, and until the material, the molybdenum sulfide merged and form a ground boundary. I think here the video will shows the picture clearly. Initially, we have a lot of nucleus, right? And molybdenum sulfide is growing bigger and bigger and push the gold at the edges. And once the molybdenum sulfide meet together, the gold will zip the edges and forming the ground boundaries. Okay, so what we can use for such structures? We use it for the hydrogen generation. Let me see. So we transfer these materials on the gold substrate, and we can find that a lot of bubbles coming out, hydrogen bubbles coming out because of the high activity of such ground boundary structures. All right, this is the okay. Let's move on. So what we can use these 2D materials in the catalysis. Actually, this was done by my postdoc He Yuming, and pretty much like this work, because we had found a very important phenomenon in the semiconductor catalysis. So we know that the electrocatalysis has been played a really important role in our daily life. So it has been like more than 100 years, right? It can be used to produce a fuel cell, the hydrogens, and many other products. However, the key materials in electrocatalysis is what is the noble metal, right? Platinum, palladium, but unfortunately they're very, very expensive. So people are thinking, can we use a semiconductor to replace these very expensive materials? So that's a lot of work. They are using different semiconductors. Of course, TMD is one of them. But unfortunately, if you look at the transport behavior of a semiconductor, we realize that if there's no gating, if there's no gate, semiconductor itself is insulated. It's an insulating. So how come the insulator can transport, okay, the electron or charge can transport into an insulate, and they realize a high performance catalysis reaction, catalysis. Okay, it doesn't make sense, right? But if you look at the research work and the publication where we will realize over the past 10 years, there are a lot of work, okay, at the high profile journals, they claim semiconductor can be also a really good catalysis. Okay, even comparable with the noble metal. So what's the problem? There's a contradiction, right? So in order to address this, we developed an in situ measurement system which can collect the signal of electrochemical reactions and also the electric signals. So this is our setup. So all the reaction will happen in very small areas. Like zoom in here. In such a small areas, we open a window. So the reaction will happen here, and the rest of them are covered by PMMA, so that we can collect the intrinsic signal from the catalyst reaction. Okay, I won't go to details. We look at the picture of catalytic reaction. We found that during the reaction, there are a lot of ions that they are accumulating at the surface, and they will generate a high field. This high field will, the result will tune the Fermi level of the semiconductor. So this picture can be described using the quantum mechanical equation, right? We can get a very beautiful result here. And the probability density of electron can be written as here, and it's only dependent on a few key parameters. Okay, the epsilon, the epsilon values, and also thickness of the 2D of the semiconductors. So we call this surface conductance. And we have carried out a lot of experiments with different thickness of the semiconductor. And it turns out during the catalyst reaction, only at the surface, we can achieve a really high current density. So if we penetrate into like 15 or 20 nanometers, the current density has been dramatically decreased by 1/10. And at around 25, it's only 100 of the maximum values. So which means for semiconductors, during the reaction, during the electrocatalysis reaction, most of the current will pass along the surfaces instead of penetrated into the electrode. So here we propose an idea of high specific surface conductance. So people they talk about the high specific surface areas, right? There are many work. Once they got a good result, they claim because of high surface areas, we have such a good performance. So this is a really general claim. But when we look at the details, we found that not only about surface areas, it's also about the surface conductance. Taking the bulk material examples, for the bulk material, when the reaction happens, here I mean the semiconductor, right? So only the surface can carry out current. However, if we can break into a lot of small pieces, very thin nanomaterials, so each flake can carry the same amount of current density. So which means that overall current density will be increased exponentially, a few order of magnitude. And this is the reason so why the 2D or why the ultra thin or the nano semiconductor has a really good performance in terms of the electrocatalysis. The last part, let's talk about the machine learning driven growth of the materials. So this work was driven by my student Tang Bijun, He Youmin, and Zhu Chao. It turns out we spend a lot of time on the growth of the materials, and it's really time consuming, right? So that we are thinking, can we use machine learning to reduce the cost and to reduce the time to making a new materials? And this is, if I look at the history of material informatics, so the routine way is we use the periodic table or some database as the starting point. Then we use a different algorithm or principle or equation to predict the property of the material, to predict the new materials, right? And the next step, we have to make it right. We have to all kind of fight on the paper. We have to make the material in our lab. And finally, we make the material in a large scale, reliable, robust, so that we can use it in the industry. So this is a life cycle of making the new materials. It usually takes more than 10 years or 5 years. And actually, this step, phase 3, is most time consuming, right? Most time consuming and the most challenging part. So how can we use machine learning to help this step? Okay, if we zoom in this, for the gross materials, here I'm talking about inorganic materials. There's, for the inorganic reactions, right? We have two different precursors, different equipment. And overall, what we're dealing with is the macroscopic parameters, such as the temperature, pressure, mass flow rate, ramping rate. So by trying again and again, we find the best parameters so that we can grow the new material. So the problem is, can we build a model and we just input this parameter into the model, and the model can tell us, can feedback the possible good parameters, so that we dramatically reduce our time. Okay, so we developed a model which is called the progressive adaptive model. And this model can be implemented into the gross material at the very beginning. Once we have parameters, no matter either good or bad, no matter the material can be grown or not can be grown, we just input the model. And the model, and one by one, the model can give us some feedback. And by doing so, okay, just this is very briefly described. By doing so, finally, the model can tell us the possible good parameters in around 100 to 200 trials. Okay, so here, taking the molecular sulfide as an example, we choose 6 features here. 6 features, 7 features here. And using this model, we realize that RT and temperature is the most important features that will dominate whether you can grow the molecular sulfide or not. And also using these models, we also demonstrate the growth of the tungsten dichloride. We can control the tungsten dichloride from the flake 2D film to the nanowire structures, as well as the 0D, the content dots. We can increase the content yield of the carbon content dots. Okay, as well as reduce the time for many trials. All right, this is pretty much my talk. And thank you for your attention. I'll be very happy to take your questions.
All right, thank you very much. I have a question, which is, these libraries are wonderful in the sense of there's so many possibilities that a person who likes characterization like me gets really excited and be like, oh, I want to try that. But with all the library that you're building, of course, the feedback needs to be on like property optimization and on actually what these properties of all these libraries are. So how much in the way have you done for, let's say, optimizing, quantum yields, or optimizing magnetic properties, or with library of magnetic materials, looking at all of the different magnetic states that are actually coming up?
Yeah, this is a really good question, right? Although we can produce a lot of materials, right? The libraries, we also think about, for example, which one is the best promising materials, which one has the unique properties. So to be honest, we don't know. We don't know. We always ask our collaborators, theoretic collaborators, okay, which one you believe that might have a unique property or good performance in terms of like electronics, in terms of like catalysis. So, and once we get some feedback from our collaborators, so that we will focus on the specific materials. So we're trying to make it even larger. We were trying to increase the quality So this is our strategy.
So I guess my question is, how do these materials compare in quality?
Oh, okay. In quality, what I can share with you is that for the same class, such as the sulfide, right? All the sulfides, they may have the similar quality, and all the selenides, all the tellurides, they may have similar quality. It's simply because, for example, when you grow the moly, the sulfide, when you grow sulfides, right?
Sorry, similar quality to each other or with respect to the exfoliated materials?
Yeah, to the peers. For example, you grow moly sulfide and tungsten sulfide, right? And we believe using the similar parameters, the material you got, you obtained has a similar quality. The similar quality means there are not a lot of variations in terms of defect concentration. Okay, but so there we cannot precisely control the quality. So I think the reason is we are still lacking of a really good understanding on the growing mechanism, And you know, right? All these materials being produced using the solid precursors, and we cannot precisely control the flow rate, and also the temperature distribution is also not uniform. So that's the problems. Okay, I think people can look at it in the future.
Okay, thank you. It looks like we have a question from Tanushree Chaudhary.
Great talk. I was just curious if you were also looking at libraries for heterostructures, or do you think there is something like that available, which again correlates it with the possible interesting, properties that they might have?
Well, yeah, for the heterostructure library, right? Heterostructure library is a little bit different with other libraries. The reason is, in order to make heterostructures, we have to make sure the two materials or three materials are compatible in terms of the melting point or the reactivity. Okay, let's put them in detail. For example, if we want to grow molybdenum sulfide and then niobium selenide heterostructure, right? We have to grow the molybdenum sulfide first, okay? Because the growing temperature is around 100 degrees higher than the niobium selenide. So if we grow niobium selenide and then you grow the molybdenum sulfide, niobium selenide will be dissolved or be just completely evaporated. So we need to choose the candidate carefully, and not all the combination will work.
Right.
And I think another problem is for the heterostructure is a little bit difficult to grow into really large scales.
Okay.
All right. Any other questions?
So my question really quickly, I will read your paper that you described towards the end on the machine learning, but I was just interested to see, like, if I understand correctly, you ran several synthesis experiments, changing some parameters guided by an ML model. Is this correct?
Yes, correct.
How many parameters did you change in your experiments, and how many experiments in total went into the study?
Okay, that's a pretty good question. So let me take this growth of molybdenum sulfide example. We choose here, around 7 parameters. So of course, we cannot, we are not able to do millions of samples or millions of experiments, right? So each of them, we change a little bit, but with a wide range. So so that they can distribute it in a large parameter space. And to make things easier, the output, we just use cannot grow as a standard. And taking the hydrothermal method example, hydrothermal method, because we are working on the conductance, right? So here, the pH values, temperature, and something like that, and precursors, they are the parameter we're choosing. So in short, usually we take 5 to 10 parameters for the machine learning. So currently we cannot handle so many parameters, right? Unless, as I mentioned, if we can introduce high throughput method to make things all automatics, so we can choose more parameters.
Thank you very much. Thanks.
Thank you, Sam.
So Zheng, thank you for the talk. My question is actually related to Sam's question also. I was curious, so in your model space then with these 7 parameters, what are the patterns that you can see from the models that tell you like what's important for determining what can grow or what cannot grow?
Okay, this also asked by our reviewers. Okay, for many times. All right, based on the model, after we feed the model like hundreds, tens of hundreds parameters, right? Then the model will tell us here which feature is more important, which is less. All right. For example here, so this temperature and RT, they're very important, which means we need to control the temperature and RT carefully, so that we can have a high chance to grow, the molten sulfide can be grown. And it's not 100%, okay, it's all about probability, So finally, okay, with the better parameters, the successful rate for growing the molten sulfide is still not 100%, it's more than 80%. Yeah, and I think the key is how do we relate this feature importance with the physical meaning, right? How do we explain this? But this is a black box, okay? This is a completed black box. So after we got this parameter, this information from the models, we have to think. We have to dig into think it. Or carry more experiments to show in physically or in the real picture, how do they relate it?
Okay, great, thank you.
All right.